All right, so here we go. So domain range stuff. Like I said, I think we can probably be a little quicker here to get through this stuff.
Oh, that one.
Domain X's or Y's?
X.
X's, okay? So we want the domain's gonna be all the X values represented in that graph. We would squeeze them onto the X axis, right? If I squeeze those up onto the X axis, where are my boundaries?
-5 and
+5, open or closed? Closed.
Brackets.
Okay, so they're gonna be closed, which means they would be brackets if we're using interval notation, right?
Yep.
So one way we could do this would be brackets, and my boundaries, my left boundary, I gotta go in order, don't I? Smaller to bigger. So, -5, 5, right? That's one way to do it. So how would I write that using inequality notation? Okay, so I'm gonna start in the middle. I'm gonna say X because that's how we'd say it. X is greater than or equal to -5 and less than or equal to 5. Okay? I want to make a point. How many boundaries are there on this interval? 2, right? There's 2 endpoints. Everybody agree? So if there's 2 endpoints, I need how many inequalities? 2. I need 1 for each boundary, right? I always need 1 inequality for every boundary. Well, I've got 2. So for example, here's one of my inequalities. That's the one that goes with that boundary, isn't it? We're saying everything greater than, meaning to the right of, greater than or equal to -5. Here's another one right there, right? So that's the one that goes with that inequality. Agreed? Okay, here, hang on. I gotta pause for just, sorry about that. All right, so here we go. So we get important connection that I want to make sure everybody's making. So we know that when we have 2 boundaries, which we're always going to have if it's like a line segment, right? If it's got to be stopped at both ends. You got to have boundaries on both ends. It has to be a compound inequality because it needs 2 inequalities, right? Every time the inequality is always going to look like that, and it might have equal signs, just depending on what kinds of boundaries they are, but it's always going to be that look, right? It's never going to look like that or something crazy, right? It's always got to go from smaller to bigger, right? We're going to get an X in the middle, or it could be a Y if it's ranged. Yes?
Did you turn the recording stuff on, or did you?
I did. I did. Thank you for checking though, because I normally probably would forget that, but today I remember for some reason.
You mobbed back inside.
I did. That was quite a mob out to the hall and back. So, that makes sense? Okay, we're good? Okay, how about this? Range. X or Y?
Why?
Y, okay.
Why?
What can you tell me about the Y here?
It's going. Infinity.
Yeah, it's everything, right? It's all real numbers. If I squeeze this onto the Y-axis, it's the whole Y-axis, right?
Yep.
So this is a weird one. How do we say all real numbers with an inequality? I gotta introduce infinities, don't I, right? So I'd say something crazy like Y is greater than -infinity and less than positive infinity. And I wouldn't put equals there, because you can't equal infinity. It's not a number. You never get there, right? It's sort of an awkward thing to have to do, but for inequalities, that's the only time I would ever use an infinity on inequalities, right? The only time I'd ever do it is if I had to say, just invoke infinities to mean everything, right? So kind of our awkward way of saying all possible real numbers, okay? What would that look like in interval notation? Okay, parentheses, good, because I can't have brackets, right? I can't include the infinity, I can never get there. And then we're just gonna have the negative infinity has to be on the left, and the positive infinity has to be on the right. It's the only way it could ever be. Yep.
I still can't comprehend how an infinity can be negative if it's already including negative infinity.
It's not, because what that means is, if this is the x-axis, That's 1, 2, 3, 4, 5, 6. Well, if I count forever, I'm gonna move towards in the positive direction without limit. Our way of saying go in the positive direction without limit is positive infinity.
Okay.
It means I'm going without end there. If I'm gonna go in the other direction, well, I could also go in the negative direction as far as I want to. If I go without limit in the negative direction, I'm approaching negative infinity. So there is a sign associated with it, because that's the positive x direction,
Just specifying
and that's the
which
negative.
way.
It's just specifying direction, exactly. Okay, how about this instead? What's the range there? Greater than -2. So there is, how many boundaries here for the y, for y? No, I wouldn't say kind of two. I'd say there's exactly one, right? Exactly one. If I squeeze this function onto the y-axis, isn't it going to look just like this? Right? How come the open circle?
Because it can't reach that.
Because it can't reach that. It's an asymptote, right? So it's going to, as we move backwards in the x direction forever, the function's just going to get closer and closer and closer to that y value. It's like I'm getting closer to the door every second if I take a step halfway to the door, but I never get there, right? So it never gets there. So there's only one boundary. So how many inequalities do I need? One, because there's only one boundary. So all I need to say is y is what? Greater than, in this case, because it's above, -2. Boom. That's it. Yes, ma'am.
I have a problem with infinity.
What's that?
If it keeps going, where can it go?
Well, I mean, it's, you know what I mean? It's the whole notion of there's no limit to never ending.
So what you're questioning is, which is our perception of infinity, that we have to describe in English words to kind of, you know. So philosophy is just fallacy in language, which I heard once, and I think it's very funny.
Yeah, but that's true. That's true. It's infinity is pretty simple. It's trying to conceptualize and think stuff. Yeah. And I think I probably said this to you before, but I literally, I'm not exaggerating. I could spend, I mean, there's so much, I spent so much time in college and in graduate school studying just infinity. I mean, we could spend an entire year and there would still be lots of stuff that we would not have even remotely covered. There's that much you can talk about. There's that many ways you can deal with it. I mean, I'll give you just a little example of something that we talk about like in calculus. Okay, so what's this? What if we have a function that looks like this? What if I'm going to take the limit of some function on the, like I've got a ratio. Say I've got something like the limit of x cubed over x squared as x approaches infinity. Yes, ma'am.
So like in the real world, when are we actually going to use graphs that are bad? That's not right.
Oh boy, I tell you, now this is something that you could use all the time. Like if you were going to look at something like radioactive decay, for example.
Okay, so like a half-life.
Like a half-life thing, exactly, yeah.
But like
Yeah.
besides like math oriented stuff.
Okay, well what about like in economics? If you wanted to, for example, if you wanted to explore the point of diminishing returns on a profitability curve or something, which is what a quantitative economist would do. You know, you'd be looking at graphs very much like that all the time. In fact, you'd be scrutinizing them because you're being paid tons of money to try to figure out what price exactly should we set for this widget that we're selling so that we can maximize our profits, and we can delay hitting that point of diminishing return, which is an inflection point in the curve. There's all this calculus that just comes into play. So all the time. There are literally, this is another thing I'll say. So when I graduated, I have a physics degree from Stanford. I graduated with my physics degree. There were all kinds of economics, how do I say it? They were looking for people who could perform quantitative analysis of economic trends. They call them quants, quantitative economists. They didn't care if you had ever even spelled the word economics. They didn't care if you'd ever taken any business or economics classes ever in your life. if you graduated with a degree, you know, from Stanford, you graduated with a degree in math or in physics, they said that they will hire you, no questions asked, and the salaries were just ludicrous. I mean, absolutely ludicrous. Say it again.
You need to do that.
I didn't want it. It doesn't sound very fun.
You came here.
Well, I didn't know, I was in,
Oh,
I was an electrical engineer for a while, and I started teaching later in life. But it's, so, I mean, there, you know, you can, if you are good at math, I promise you, if you're good at math, there is, and you wanna make money. I mean, and money's, and I will tell you, I don't think money is everything, it's really not. But if you're interested in making lots of money and you're good at math, it's not hard to do. I mean, the starting salaries were, you know, deep into the six figures, that's right after college. You know, and they were gonna, now, there were some downsides to it. I mean, you had to move to the East Coast, and you had to, you were gonna work, the hours were gonna be pretty bad. You're gonna be probably working 60-plus hours a week. It was gonna be pretty brutal hours, but it was, you know, and I don't know, I mean, it's not, morally, you have to ask yourself, if you really wanna support that kind of, I mean, there's other things that go into it too. But it's, in the real world, yeah, this kind of thing is absolutely something that's used all the time. And it's, if you know how to do it well, you can be highly compensated if it's something that you wanna, you know. And not even just in this kind of thing, like if you were looking at something like, being, you know, a statistical analyst or an actuary, you don't even have to be that good at math. You just have to have had enough of it that you can do that analysis, and you get paid a lot of money right out of college, you know. I mean, a lot of money, good benefits. So yes, this stuff is out there. It's not so arcane that it's not, this isn't just for geeky guys that, you know, I mean, it's, that are staring at computers all day. People will pay you a lot of money to do this stuff because not very many people can. And so if you get to where you can, that's a hugely valuable skill to lots of people.
Why don't they just use a Desmos?
Well, they use things a lot more powerful than Desmos. They use computer algebra systems. But the computer algebra systems, it's like, I mean, when we get into calculus, we get to a point in calculus where a lot of the problems that we do, you know, we learn the calculus, but at some point, it's about understanding the concepts of the calculus. And I'll have tests where you can use any graphing technology you want. I don't care. In fact, I'd encourage you to. I don't want you to get bogged down with trying to do the intricacies of solving this quadratic. I know you can solve a quadratic equation. Just do that use graphical tools to do that. But the point is, the problem is really a difficult, involved problem. And so to be able to come up with a strategy for solving the problem, you have to understand how to use all these tools, how they apply to the problem. Does that make sense? It's not so simple that you're just gonna, knowing how to use the technology, great. But knowing how to use the technology to solve a complex problem, you gotta know a lot of math to know how to approach that, right? So that's really what it's about, okay? So, but you would use, Desmos would be, that'd be small potato. You'd use something a lot better than Desmos. You'd
I'm
use.
still on TI-30, so I'm a little behind. I'd probably still need it.
Yeah, well, Desmos is the next thing. There you go. Let me give, baby steps, baby steps. All right, so y is greater than -2, right? We only need one inequality for one boundary, right? Now, how would we write that using interval notation?
I'm an idiot.
So if it's greater than -2, you tell me, is this a lower limit or an upper limit? It's a lower limit, isn't it? The boundary's on the bottom, isn't it? So doesn't that mean then that we're gonna have to have the -2 on the bottom? Right? And then infinity, right? Because it's a lower limit, there is no upper limit, so we're gonna put an infinity there. It goes up forever. Make sense? Okay? How about this? Use one or more inequalities to write the intervals on which the function is decreasing. Okay? So now, so here's an example. Like these are not, there's no computation to do on these problems at all. There's no algebra to do at all. It's just a matter of, but you gotta use your brains to analyze the function. You gotta kind of know what the concept of increasing versus decreasing is and how that applies to a graph, right? It's just all thinking. Okay? Well, how's it work? What does it mean to be a decreasing function?
It goes down in value.
Okay, down in value or downhill from,
The original highest point? Peak.
so downhill, but, okay, so that's walking downhill, but what's wrong with that?
Or just go to positive zero.
Oh, okay, in the, in the positive x direction, right? From left to right, you're walking downhill. Negative slope, in other words, right? So that would be, if we identify those places on the graph, would you agree that that's gonna start, right, it's level right there, so that's where it starts, right? And it's level right there, so that's where it ends. Every place in between is decreasing, you agree? So if we squeeze that onto the x-axis, which is what we're being asked to do, and I'll explain why in a second, then that's the interval, right? Now let's read this question carefully, because it's time for us, you're kind of one of the next steps in becoming a college level math student is being able to understand the language of math in a way that's meaningful. You can interpret it and know what to do, right? So it says use one or more inequalities. So what kind, our answer is going to look like less thans and greater thans and that kind of stuff, right? We're going to use inequality symbols, right? To write the intervals on which the function is decreasing. Well, what's that, intervals? So we want to know, that's an interval, isn't it, right? We want to write the parts of the domain, the sets of values of x, right? The groups of x values that are going to correspond to where the function is decreasing, right? Well, it's decreasing from there to there, so that's the interval in question. We're talking about x values, though, right? Only if we're asking for range specifically would any of these questions be referring to y values, right? We're always wanting to know for what input values, for what x values is something happening. Well, what are the x values there? Now, how many boundaries are there? 2, so we know it's going to have to look like that, right? Well, what's my lower boundary? Looks like it's 1. What's my upper boundary? Looks like it's 5. We're done. Okay. Now, what if it said instead, actually, we'll just move on. We'll use this one. Here's a good one. So where is this function? Use one or more inequalities. So we know we're using inequality symbols to write the places or the intervals on which the function is positive value. So think of, ask your brains, where is the function positive value? Where it's above the x-axis. Good. That's the part of the graph we're looking for. Well, doesn't that start? So it's above the x-axis right there, isn't it? So it starts there and ends there. So there's one interval. Okay, and where else? Okay, and then up there forever, right? So it starts there. How many boundaries on that interval? One, so it just goes forever, right? Okay, so here's an interval with 2 boundaries, so it's got to be a compound inequality, an and inequality. So that one's going to be x is greater than 2 and less than 4. Agreed? This one has how many? 1. So all I need is just one inequality, or x is what? Greater than 6. Okay, but here's the other part of this now. How many total intervals do we have? 2. We have 2 total intervals, and so what has to go in the middle? You have to have an or statement because they're different intervals. You can't be here and here at the same time, right? That's not the way the world works. Well, actually, in quantum mechanics it does, but we don't live. We're not atom sized, so it's quantum mechanics. We'll talk about that later. But mathematically, you can't be in both places at the same time. You can only be in one place at the same time. Any x value that you choose is either going to be there or there, but never in both, correct? So we have to have that or symbol in between. Okay? Whenever there's multiple separate intervals, we have to consider that we have to connect them with ors. Okay? All right, what about this? Right, the end behavior. So end behavior just means we want to know what's going on way out yonder and way out yonder. Right? So on a, we don't really care about what's happening in here. We just want to know what's happening clear out there and clear out there. So how do we interpret this statement then? If we say something like, as x approaches negative infinity, that's x is the horizontal or vertical variable. Horizontal, right? It's telling us the horizontal components of every point in the plane. So we want to know horizontally speaking, in other words, as x, how did I say this last period? I thought I kind of liked it.
walks.
And you can't walk.
Yeah, what did I say? I was good. Now I can't remember what the heck I said, but it was pretty good.
While you're looking for it, can you explain to us the thing about walking?
No, it takes a little more than 2 seconds. We'll talk. I promise you. Remind me on another day, and we'll talk about it. It's pretty cool stuff. So. Oh, dang it! This is-
Parabolas and more parabolas.
Oh, I accidentally deleted it. Shoot. Okay, so. Okay, here's the way I can tell you. This will work. So as x. As x goes to the extreme left, right? We're going clear out to the left as far as you can go. What does y do? That's all it's asking. F of x just means y, so it wants to know horizontally as we go to the extreme left, what does the function do vertically? Yeah, it goes to the extreme bottom, right? It goes down forever. So you can see that as we go this way, we go that way. So the answer is negative infinity, right? Okay, how about this one? As x goes to the extreme left, what happens now? Negative 2, right? It doesn't go anyplace crazy. It just gets closer and closer and closer to negative 2 the further we go to the left, right? So we get negative 2. Because as we go this way, it's just getting closer to that value, right? Okay, this stuff. So this is an example from the other day, but I bring it back up because it's so useful. Now we talked about, we had some crazy talks here a little bit ago about economics. In real life, people don't really do algebra very often. You don't. Most of the time you use technology to solve equations. You would do stuff like this. This is what you would do in the real world. You would use something like Desmos or Mathematica or a graphic calculator to find the real, as long as you're looking for real solutions. Now, if you're an electrical engineer, you might be stuck doing some algebra because you might need the imaginary solutions, right? But if you're looking for just real solutions, which oftentimes you are, you can always use the trick that we've talked about. All you ever have to do. And it can be the craziest equation in the world. It could be combinations of, like, you could take a logarithmic function of the 5th root of some bizarre trig function, right? It doesn't matter. I mean, you could have that equal to something else crazy on the other side. But as long as you use this trick, you can always find the solutions graphically. If I graph whatever's to the left of the equal sign, so y equals whatever's underlined in red, there it is, right? I graph, and then separately from that, I'm going to graph y equals whatever's to the right of the equal sign. So Desmos is nice because the color graphs really help. So we get the red graph, looks like that, and the blue graph looks like that, and all we're looking for are the intersections of the two graphs. That's it, right? The intersections of the two graphs represent, hey, I'll tell you what, let's get the Chromebooks closed, and earbuds should obviously not be in, right? Let's get rid of those. Because if you got earbuds in, that means you're probably not soaking in as much math as you possibly could. Right, so earbuds should all be out, all the way out. That should be nice, thank you. And so here are the intersections. Well, we're trying to solve for x, aren't we? Right? So we just need the x coordinates of the intersection, so negative 3.6 and positive 2.2. There you have it, right? That's it. Now there is a little bit, these can be a little bit tricky. Like I'm going to skip around just a little bit. Let me skip up to that one. Yeah, that's kind of handy. You want one of those on the test? Yeah. Okay.
I like that.
You like that?
Yeah, because I have
I know you
two
can keep your little
separate
fingers
screens now.
Yeah. Sometimes it's a little tough, I agree. And there is a little bit of an art to using this technology too. So what about a problem like this one, right? Now, sometimes I know I pick the parts of the graph where it looks pretty darn, it looks so obvious, right? And it doesn't always start that way. So let's talk about a problem like this where maybe, how can we get our graph to look something like this so we can see the solutions better, right? Just kind of the pragmatic parts, the practical parts of using the technology. So we know the strategy, right? We're going to set whatever's on the left equal to y, and whatever's on the right equal to y. So we get a blue curve and a red curve and look for the intersections. But if I actually do that, here's what the graph starts off looking like. The graph starts off looking like this, okay? That's if you just start with the normal home screen. Like if I move this around and then I click home, it always takes it right back to centers everything, right? So that's not very obvious. You can't see where they cross. Well, if I drag this thing down a little bit, you kind of get a sense that they're crossing in there, but it's hard to find the exact places. How do you make that look like that, right? So yeah, I mean, the trick is just to sort of zoom in, right? But there's even a better trick I'll show you. So to zoom in, I'd want to maybe or zoom out maybe at first. Okay. Yeah, now the dots are in here somewhere. If I want to, what I really would like to do is kind of not zoom in vertically. Leave the vertical alone, but zoom in horizontally, right? Kind of, you see that if I were to take this thing and I were just to sort of spread it out horizontally, those lines might separate a little bit. There is a way to do that in Desmos. So all I have to do in Desmos is if I go up to the little wrench handle up here, the graph settings, I can manually set where the left and the right edges of the graph are. So doesn't it look like, let's see, there's -10. So maybe if I were, let's see, if I were, what do you think? Like if I set my left edge at something like -11 and my right edge at something like, I don't know, how about -6? I could really spread that. You see, I'm just looking down here at the bottom. You see those numbers? So let's try that. If I make the left edge become -11 and the right edge, oops, I picked the wrong one. Darn it. I was doing y's instead of x. I do that all the time. Let's try that again. So the x's go from -11. Oh, maybe it was that. Oh, I'm seeing things. Yeah, I was doing it right. Never mind. And -6. See, that helps, doesn't it? Now I can see that there's an intersection right there. And when I click close to it, Desmos is smart. It knows that I'm trying to find intersections. And so look, it already kind of shows me where the other dot is right there. Everybody get that?
It like pities you. It's like,
It
oh,
does. It
well,
does. It frequently pities me. It needs to. Okay, you get that? But here's the other trick. What kinds of places does Desmos even show you? Desmos shows you, like if I zoom in down here, it's going to show me intercepts. So it's going to show me, there's one that's an x and a y intercept. There's another one. It shows me the minima and maxima of curves. So there's a minimum of that curve. It doesn't just show me random places. If I try to click there, it doesn't stick because there's nothing important going on there, right? But the other place it tends to show me, like there I can find one because there's a y-intercept. So there's an important point it'll stick to, right? But the other kinds of places it shows me are the intersections of curves. So if I think there's there's one sort of around in that area, if I just click around, yeah, look, it gives it to me. And furthermore, if I were like to zoom out then, and I say, okay, well I know there's one there, there's the other one right there. It automatically knows. It shows all the other ones. Once I click on one of them, all the other ones pop up in light gray. You get it? So I know, what else could those be? Those have to be intersections of the curves, even if I can't tell from the graph, because it doesn't resolve the differences in the blue and the red there very well. That's all they could be. They're not intercepts, right? They're not x or y intercepts. They're not minima or maxima, not a minimum or maximum of the curve. So it has to be an intersection, right? Okay. All right. So then questions like this guy. So on these are really simple then, aren't they? This is the same kind of thing. we want to solve this equation. That's what it wants us to do, solve the equation. Well, really, all we're going to do is we're going to graph the left side. Now, I don't know what f of x is, so I can't actually graph it on technology, but the math gods did it for me. The function of f of x is right there. It's below. That blue graph is the graph of the left side of the equation. So all I've got to do is graph the right side. Hey, what do you know? There's a little line just happening. How about that? So I can graph the line y equals -2. It's right there, right? Now, you don't probably have to actually graph it. You can do that in your mind. You're just trying to find the place where the function has a y coordinate of -2 is what this amounts to, isn't it? So we're going to get one intersection right there and one right there, and all we care about are the x coordinates. So what's the x coordinate at that point? -7. What's the x coordinate of that point? There's the answer.
Ooh,
Right.
that's expensive, Mr. Ward.
I know, I shouldn't do that.
Control yourself.
All right, let's call her good for now.
Use it.